Hello everyone, my name is Braun. I'm part of the R&D team that's been bringing you USRPs for quite a while now. And I've often spoken here at GRCon to present new products that we've been working on or new innovations that we've created. But not this year. This year I want to do something slightly different. I've asked a couple of other members of the R&D team to join me here and just talk about their work for a bit. To give you some insight in who are the people behind the USRPs and what are some of the things that we are currently working on. And I think without further ado, I'll just head straight in there. My first guest is Jan from the NI Dresden site in Germany. He is responsible for the architecture of the X410 USRP hardware, and he has some knowledge bombs for you.
Right, I'm Jan Schirok, product architect of the X410. So that means I'm bringing together hard and software, making sure that some of the requirements that you guys have are met, and also that our development is going in the right direction. And today I want to talk about something very general about an architecture. And this generalism is basically around superhead IF or zero IF IQ architectures. And for X410, we've deliberately chosen an architecture that is now a superhead design. So we're using ADCs or DACs that are sampling at an IF frequency. Sampling that also means we're filtering it. Then we're doing an up conversion to a filter bank and doing potentially for carrier frequencies below 3 GHz, a down conversion again. And for that, you need another filter bank. And this is basically a superhead design. Most of our USRPs before, and many of the other architectures you find in this space are actually zero IF systems. So they're IQ based. There are two ADCs or DACs, and they go into an IQ mixer and then to a filter bank. And so the general aspect why we've chosen the superhead here for this design is that you get a cleaner in-band spectrum. So what that means is this IQ architecture, and I show that in the next slide as well, is basically showing you images in the spectrum that you're not, if you don't correct for them, are actually degrading your EVM performance and show up as lines that you really don't want to see in your spectrum. And so this is kind of one of the main reasons we've gone to the IF-based architecture. Mixers and synthesizers wise, it's still one or two that you've got there, which is, for example, for the UBX, the same. So there are also two mixers and two synthesizers are used for a certain frequency range. It's just one ADC or one DAC that you are using in IF for high sample rate here, which in comparison, IQ would have two of them and then at a moderate rate, but a well-synchronized I and Q scheme that works that way. And there are some complexities as well, and I come to the frequency planning side of things in a second, and also RF filtering is obviously something you have to take care of. Whereas in IQ, the main challenge is really finding the right IQ mixer that covers all the frequency range that you have, which is the challenge for the wide ranges we want to hit. And so the ideal in-band spectrum you see on the left-hand side, and it is idealized, so IF-based, even that will show you some spurs, but those are usually from out-of-band mixing products. So the in-band spectrum is actually pretty clean that you get. If you're seeing the same spectrum in an IQ-based mode, and you've probably seen that spectrum already in a lot of plots you've seen for IQ-based systems, is that you get this DC offset, even though no signal is around, or kind of an image rejection, so a kind of a mixing product there. And this doesn't even incorporate nonlinearities in the mixers. So if those are added, there's even more spurs that you're seeing in IQ-based architectures. For them, obviously in-band. So the challenge that you're running into if you're doing that, and that's the tricky side of things, which is why we're not doing that IF-based architectures in all the products we have, is it's a challenge to actually cover the wide frequency range. So our ZBX in X410, the dot code there is 1 MHz to 7.2 GHz. So that even tunes up to 8. And you see the frequency plan here on the left-hand side. And you can look that up, how we've put things together. you've got for every single frequency selection, you've got I frequencies to choose from, you've got LO frequencies to choose from, and you've got filters in each filter bank. So a lot of design complexity there. And that design complexity you also see in kind of the block diagram that's also in our knowledge base. And so there you see per channel, our ZBX contains 4 synthesizers to cover GX, RX, 20 amplifiers, over 40 filters. So 4 of them even, that's just one channel, right, in the X410, which is a lot of RF to put on a board. And that is one of the complexities in the design, to actually put all of those components onto a board and make them work with each other and together. Right, that's my short intro on IF and IQ-based architectures. We've deliberately chosen IF here in order to get kind of the good and clean in-band spectrum, but that comes with a lot of complexities.
All right, and my next guest is also from the Dresden site. His name is Volkan. He's a hardware engineer working on the analog design of the actual device. He also does other things such as testing, oversight, but he's going to present a couple of new features of the X410 for you.
My name is Volkan Etz. I'm an analog design engineer at NI. I am responsible for either designing new USRPs and helping also with customer escalation. So whenever there is a bug in our hardware, usually I'm the first one looking at this and distributing to the team. And especially this year, I was working with the team on supply chain issues we had, so replacing components so that we can still deliver the products. For the X410, our latest USRP, I have worked on the motherboard design, especially, so the RFSoC, and spent a lot of time on V&V to make sure that the design meets all the requirements we had and that we have characterized it accordingly so that we have a clear data that we can present to customers. So today I want to highlight a few upgrades we have done to the USRP, and I want to start with the first one here. This, especially on X310, I think we got on a weekly basis the question how the customer can make sure that the device is working on really heavy environments. Because of this, we have added a lot of monitoring to the X410. So as you can see in this simple block diagram, we have a microcontroller which is monitoring all voltage rates. It's monitoring the power. We have added a lot of temperature sensors on critical places on the PCB, so that these can be all taken to monitor the device and also to control the fan in case you want to go to higher temperatures. Moving on, the second feature, it's the GPIO interface. So we've moved on from DB15. We've increased the IO lines or doubled them. And now we have a maximum data rate of 100 megabits per second and selectable IO voltages. So this way, hopefully customers can now work with a faster interface to control devices which they usually want to control with an USRP. These can be external RF modules or antennas. Maybe there are other things. So, and this improves a lot of things. We can use the HDMI cable and don't have to rely on the DB15 cable anymore. Then moving on to some clocking improvements we have done. We have an TI PLL chip inside, which we now used fully. Especially used some divider resets and some special modes which a PLL chip enables to improve the phase coherency performance of the device. So whenever you're using a USRP, the phases are by every reboot, by every restart, it's different. And now we want to improve it. There's still work in progress. This is not finished. We're still learning about this complex system. and are trying to improve it even more. We have over 10 PLL chips on this, so getting all of them together, it's a challenge. And the last thing I want to mention is that we have gone away from the SD card slot. So we are using now an internal eMMC, which is on the motherboard, and I haven't measured it, but it feels way faster upgrading file systems. So for our customers who have to change it daily or often, this is something which we have improved definitely. And yeah, with that, I finished highlighting the small features we have, the team has worked on and upgraded for this release.
And I have one more guest from Dresden, from Germany, Lars, who is part of the software team working on new features to make access to USRPs and UHD more easy. And he will be talking to you about C#.
Hi, my name is Lars Amsel. I'm working for the UHD software department for about 2 years now. And in these 2 years, I mainly worked for the X410 software platform and for calibration of the USRPs and things like that. What I want to show today is how difficult it would be to have .NET access directly for the UHD. So what was the motivation? So it's UHD is written in C++, and we have API binding for Python and C. And as long as you stay in this world, everything is fine. But if you want to use .NET, specifically C#, then the only easy way is to use the C API by pinvoke, and that's quite cumbersome, especially if you want to use the object-oriented features you have in C#. And of course, the UHD is written object-oriented, so it is not a nice way to go over the API. And the other thing is that the C API is only a subset of the multi-user and has no RSNOC support. So the idea is to have a .NET API that wraps multi-user and RSNOC, and that would easily use from any .NET language. What I did in the proof of concept is I had a look at some automation tools, but had difficulties to get them working together with the plain UHD. So I didn't want to change so much on the UHD DLL itself. And UHD makes a lot of use of concepts from standard lib that are not allowed in .NET, like mutexes, threads, and so on. And also, I didn't want to add additional dependencies for the UHD itself. So what I used at the end is the C++ CLR. That's a C++ dialect Microsoft invented for the .NET world. And this one is ideal for wrapping C++ DLLs in .NET. So what you can do, you can in your implementation, you can just use the C++ DLL as it is. You only have to make sure that all your parameters, return values, and so on, that they conform to the .NET world. And so there was not much need to adapt the UHD DLL itself. So some header files had some links to mutex and so on, but it was easy to solve. So when you use that, so because in UHD we use a lot of smart pointers, you have to make sure that you use a smart pointer like concept in the .NET implementation as well. Then everything is mostly a simply wrapper. As you can see here for the ZRX antenna, it's just a call to the user object, and that's it. A bit more difficult is when you have non-primitive types, but at the end of the day, it's just work to do. And so UHD uses a lot of exceptions for error signaling. These does not leave the boundary to .NET. So in .NET, you will only see a generic exception in that case. So that would be something we would also have to spend more effort on having a good error propagation into the .NET world. But at least array handling is quite easy because we don't need an additional copy in that glue layer. So, and what I can show you now is, on the one hand side, how the C# program looks like. And if you are familiar with the Python one, that might look fairly familiar to you. So you create the object, you set different properties of the object to meet your need, and then you can just create a streamer, issue a stream command, and with the buffer you create, you can just call a receive on that. So it's quite easy and fun to use. And I have the same program in LabVIEW as well. So LabVIEW in that case, because it was easier for me to have a running plot in that. So just create the object, then I set all the properties. I get the streamer object, call the issue stream command on that, and in this loop here, I just call receive again and again and display the result in a graph. So I'm going to start that. That takes some time to start, and then you will see I have a small signal generator on the RX, and you see I can easily receive. So why do I present that? So we are not decided yet whether we want to create and maintain an additional API for UHD, in this case the .NET API. It would be very nice to get some community feedback, whether this is interesting for you, whether you would like to use something like that, so we have some feedback and can make good decisions on whether we want to support .NET or not. Thank you for your time.
And finally, I have someone from the Austin side, of course, from Texas, Humberto, a digital engineer who is currently and for the foreseeable future working on new features for USRPs. And his desire is to bring data to you as fast as possible. Let's hear it from Humberto.
Hi, everyone. My name is Humberto Jimenez. I'm a digital hardware engineer working for NI in the SDR products, specifically USRPs, which I am very excited about. And today I wanted to talk to you a little bit about one of the key features that we have in Export 10 from a digital perspective that will enable a lot of applications with the high data throughput. And what I'm talking about is 100 gigabit Ethernet. So I prepared a few slides just to give you some visual aid here. But this is essentially what I'm talking about. So at the Export 10 level, we have very capable hardware. So this is a picture of the rear panel of the module. We have two QSFP connectors, as you can see here in the back. Two QSFP28s actually. Each of those connectors has 4 MGT multi-gigabit transceivers per connector, and now each MGT is rated up to, or analog rated up to 25 gigabits per second. So that is what essentially what I'm trying to do is we have a lot of data capability or data movement capability in the Export 10 and expandability, right? So we could have up to 200 gigabits per second of aggregated streaming bandwidth. Now, what are we doing with this? Well, first thing is 100 gigabit Ethernet, getting that implemented, and that's what I'm talking about here. So sorry, I'm a digital engineer, so I'm a little bit biased towards digital, so I'm going to be mostly focusing on the FPGA side of things. So we had a concept in the Export 10, which is using a well-defined architecture, and we applied this to the implementation of 100 gigabit Ethernet as well. So this is just a diagram for reference. We have the QSFP28 connectors on the right-hand side, and we have RF NOC infrastructure on the left-hand side here in the diagram. We have an embedded ARM Cortex A53, and the transition of logic and data between these pieces is well defined in the architecture. But also, in order to be able to support different protocols and combinations like 10 gigabit Ethernet, like we do in our shipping FPGA currently, or 100 gigabit Ethernet, which I'm talking to you about here, we made this data pipe here, the blue data pipe cheddar, adjustable at compile time. So we can either optimize for footprint, which is a 64-bit cheddar width, that's for the 10 gigabit Ethernet, for example, or we can make it as wide as 100 gigabit Ethernet requires, which is the 512-bit. So that is going to be optimized for throughput. The other thing that we have in our well-defined architecture is an RX pausing capability. So now the X410 can request the host to stop sending Ethernet packets. Now let me move on to another cool thing about the implementation of 100 gigabit Ethernet. We started using more about system Verilog in this implementation. So at a test bench level, we have a lot of permutations and combinations that we are testing on the QSFP wrapper that you saw in the previous slide. So we're testing, for example, 10 gigabit Ethernet, 100 gigabit Ethernet, and several combinations of those. You can see here even the cheddar width is being tested, right? So this can be easily expanded upon the required application that our customers have, which is great. And also tagging along with the well-defined architecture and easier to implement things, we started to use more of the AXI interfaces. So we have AXI full, light, and stream interfaces defined that we are reusing across our module descriptions. So you can see here from the previous diagram, those names that I highlighted in that diagram exactly translate to this interfaces. Instead of having like all the signals for AXI full, for example, which is a long list, we are compacting them into pretty interfaces here that are easier to follow along and to expand as well. So this makes our design more modular, which is something we are really proud of. Obviously, with high speeds like 100 gigabit Ethernet, there's some challenges like timing closure. So we had to do a lot of pessimistic placement and routing as well, but that didn't cut it by itself. So one of the tricks that we are implementing in our build script, specifically for 100 gigabit Ethernet, is we are tricking Vivado into making our placement a little bit more pessimistic. And then right before we start routing our design, then we tell, hey, forget about that pessimistic directive, so that it has better timing closure. Now, current state of affairs, performance with DPDK on a fast computer with recommended settings, we have been able to get up to 32 gigabits per second from X410 to host. And from host to X410, we were able to get twice that. So 4 channels of the 400 megahertz of bandwidth, RF bandwidth, I mean. So we're still working in this feature. We have a lot of great minds making progress into getting this finalized to customer and public standards. We actually do have a preliminary support in our current UHD release. However, we are working on finalizing some of the drivers for the embedded ARM and UHD support, and also making the FPGA timing closure easier with 100 gigabit Ethernet and the 400 megahertz of bandwidth logic. So yeah, I'm pretty excited to see what customers are going to be able to do with this type of streaming capabilities in the future once we release the full 100 gigabit Ethernet feature.
All right. I hope you enjoyed meeting the R&D team together with me. I hope we could show you some of the new things that we are working on. And yeah, I'd like to thank all of you for watching this video and having a look at the new features that we either put into the X410 or that are coming potentially in the future. And if everything goes well, we might have people on site to answer questions. But I'm going to hand it off to those and back to the hosts. Bye-bye, everyone, and until next year, hopefully in person.